To someone observing a large train of wagons being pulled by a diesel locomotive, it may seem simple. A powerful engine at the front of a train, pulling thousands of tons across vast distances. It looks like a massive version of a truck, loud, heavy, and built for strength. But inside, the reality is far more complex, because unlike most vehicles, a diesel locomotive doesn't work the way you might expect. It doesn't simply use its engine to turn the wheels. There is no direct mechanical connection, no traditional transmission sending power to the axles. Instead, what happens inside is something closer to a mobile power plant, a system where energy is constantly being transformed from fuel to motion through a process that is both elegant and highly engineered. And this process doesn't happen in a straight line. It happens in layers, with multiple systems working together simultaneously, adjusting, responding, and optimizing performance in real time. So what actually happens inside a diesel locomotive? How does it convert fuel into the force required to move thousands of tons? And why was this system chosen over more direct mechanical solutions? To understand this, we need to go inside the locomotive and follow the flow of energy step by step. But before, if you enjoy engineering explained in a clear and realistic way, leave a like, subscribe to Rail Tech World, activate the notification bell, and share your thoughts in the comments. Your support helps us continue exploring the hidden systems behind modern infrastructure. The core principle at its core. A diesel locomotive is not just an engine, it is an energy conversion system. The diesel engine does not directly drive the wheels. Instead, it powers a generator, which produces electricity, and that electricity is what ultimately drives the train. This configuration is known as diesel electric propulsion, and it defines how the entire locomotive operates. Because once energy becomes electrical, it can be shaped, controlled, and distributed with precision across multiple systems at once. The diesel engine, at the heart of the locomotive, is the diesel engine itself, a massive internal combustion system, engineered not for speed, but for sustained power output. These engines operate within a narrow range of RPM, optimized for efficiency and durability. Unlike cars, where engines constantly change speed, locomotive engines maintain stable operation. While power output is controlled elsewhere, this is a key difference. The engine provides energy, but it does not directly control motion. That responsibility belongs to the electrical system. The generator and energy transformation, connected directly to the engine, is the main alternator. As the engine rotates, the alternator produces electrical power. This is where mechanical energy becomes electrical energy. But this electricity is raw, unregulated, and not yet usable for traction. It must be conditioned, shaped, and precisely controlled before it can drive the motors. Power electronics. This is where modern locomotives become truly advanced. Power electronics act as the brain of the energy system. Rectifiers convert AC into DC. Inverters convert DC back into controlled AC, allowing precise control of motor behavior. But more importantly, they allow continuous modulation of power, adjusting torque output instantly without changing engine speed. This means the locomotive can respond to changing conditions without mechanical delay, climbing a hill, starting a heavy load, or maintaining speed. All are handled through electrical control. In real time, traction motors and axle control. The conditioned electricity is delivered to traction motors, mounted directly on the axles. These motors convert electrical energy back into motion. But unlike traditional systems, each motor can be controlled individually. This allows the locomotive to distribute power dynamically across multiple axles. If one wheel begins to lose traction, power can be reduced instantly on that axle, while maintaining force on others. This level of control is impossible in purely mechanical systems. Advanced traction control. Modern locomotives continuously monitor traction conditions. Sensors track wheel, rotation, axle speed, and even micro variations in movement. If slip is detected, the system reacts immediately, reducing torque, adjusting current flow, and restoring adhesion, all within milliseconds. This creates a self-correcting system where traction is constantly optimized without input from the operator. Dynamic braking, one of the most fascinating processes inside a diesel locomotive, happens when the train needs to slow down. Instead of relying only on mechanical brakes, the system can reverse the role of the traction motors, turning them into generators. As the train moves, the wheels drive the motors, which then generate electricity. This energy creates resistance, slowing the train and converting motion back into electrical energy. In many locomotives, this energy is dissipated as heat through resistor grids, often located on top of the locomotive, with large cooling fans removing excess heat. This process reduces wear on mechanical brakes and provides smoother, more controlled deceleration. Thermal management systems. With so many energy transformations, heat becomes a critical factor. The engine produces heat through combustion. Electronics generate heat during conversion. Motors produce heat under load, and dynamic braking creates even more thermal energy. To manage this, locomotives use complex cooling systems, including radiators, fans, coolant loops, and airflow channels. Temperature is constantly monitored, and cooling is adjusted dynamically. To maintain safe operating conditions, fuel and combustion precision. Fuel delivery inside a locomotive is highly controlled. Injection timing, pressure, and quantity are all precisely managed. To ensure efficient combustion, modern systems use electronic control units to optimize fuel usage, reducing waste and improving performance. This is especially important over long distances, where efficiency directly impacts operational cost. Auxiliary power systems. Beyond propulsion, the locomotive powers multiple subsystems: air compressors for braking, battery systems for startup and backup, lighting and onboard electronics, control systems and diagnostics. All of these rely on the same energy flow, making the locomotive a fully integrated power system, not just a vehicle. System integration. What truly defines a diesel locomotive is integration. Every component is part of a continuous loop. The engine generates energy. The alternator converts it. Electronics regulate it. Motors apply it. Sensors monitor it. And control systems adjust everything in real time. This creates a constantly adapting machine, capable of responding instantly to changing conditions. Load variations, track gradients, weather conditions, all managed without interruption. Why diesel-electric still dominates despite advances in technology. Diesel-electric locomotives remain widely used because they offer unmatched flexibility. They can operate without external power infrastructure, handle extreme loads, and deliver reliable performance in diverse environments. Their design allows scalability, ease of maintenance, and long operational life, making them one of the most practical solutions in modern rail transport. At first glance, a diesel locomotive may seem like a simple machine, but inside, it is a highly sophisticated energy ecosystem where fuel is transformed into electricity and then into motion. Through multiple stages of control and conversion, every system is connected, every process is optimized, and every movement is the result of precise engineering. Because in railway systems, power is not just produced, it is managed, directed, and continuously refined to move thousands of tons with efficiency, reliability, and control across every kilometer of track.